You can't tell me for 1 second that if we put our minds to it as a species, that we can't get that thing built. And use the existing materials. It's fine. It's fine. Because in the meantime, we've got computers. We can model down to the atomic level what this stuff is going to do. We have huge numbers of world-class scientists at the 22 national laboratories here in the United States. We can partner up with the Czech Republic. Jan Ulich is doing some fabulous work in Prague right now. David LeBlanc is doing some outstanding work in Canada right now. Let's do it. We can do it in 5 years, 6 years, without question. With enough money and enough will, we can do it, because we definitely have the brain power. Definitely. A molten salt reactor, particularly either a uranium or a thorium one. I prefer the thorium one, but it needs a kickstart. It needs a kickstart. And there's this thing called K-effective, whatever. You need enough neutrons around to keep the thing going, the so-called chain reaction. The way the molten salt just kind of works is that it is a very efficient expenditure of that fuel, okay? Because unlike solid fuels, everything's kind of swimming around in a soup. And so you get like fabulous surface area with that. And you get really lousy surface area with a solid fuel. You also get a very incomplete utilization of those solid fuels. And there are very real, very direct technical reasons, which I'm not going to go into, as to why. The fact that a molten salt reactor is a liquid means, by definition, you're going to have extremely efficient expenditure of those nuclear fuels. That's great. Well, what is the water in your car doing? It's a liquid and it's transferring heat, right? In the example of your car, you want your motor to be operating at as low a temperature as possible, because for your motor, heat is a bad thing. If you're a human and you want to generate a boatload of cheap electricity, and you want to do a whole bunch of other things that is good for humanity, you want as much heat as possible. And you want extremely efficient heat transfer. So whether it is your car or whether it's a nuclear reactor, you want extremely efficient heat transfer. That's why you want very good fluid dynamics inside the motor of your car, because you want as much heat away from that engine as possible. Same thing here. We want efficient heat transfer, but in this case, we want to move as much heat as possible toward whatever we're trying to heat up. And that's what's so great about a molten salt reactor. So the fuel is its own coolant. And that's tough for people to think about, right? Because you got gasoline in the back of your car, and that's your fuel. And you got water, and that's your coolant, way up in the front. And never the twain should meet, right? Or else you'll have a real mess on your hands. So it's really tough for people to get their heads around that idea, where the fuel is its own coolant. You are moving the fuel, and it's that very act that is permitting you to get rid of that heat and use that heat in a very efficient way at the end with a heat exchanger. And to heat up, you can do it in a number of different ways. You can heat up another fluid or two fluids, and you can get that heat to be transferred into a turbine, because you can make steam with that. The steam will make the turbine move. You generate electricity in that fashion. Fabulous. Everybody's happy. So that's why a molten salt reactor is so efficient. Nuclear waste, as what is historically or classically thought of, basically comes in two forms, okay? Spent nuclear fuel, okay? It's in the form of these pellets, okay? And these are the fuel rods, okay? And those are little pellets, okay? They are around 4 to 5% enriched, okay, of uranium-235. The waste stems from, those are incompletely used, okay? Those are not used to completion, okay? The way we do it right now is, again, poor design. I mean, those are not used to completion, okay? As a result, there are two forms of nuclear waste. There are those unspent, uncompletely utilized fuel rods, okay? And those have two things: fission products, okay, and I'll go into what those are in a second, and so-called transuranics, okay? When the nuclear reaction occurs, you get things, you get elements and isotopes that are bigger than uranium. You keep adding and going up and up and up. That's why uranium is not the last element in the periodic table. It's not the last element, okay? There are many elements that actually occur after uranium. And the reason is that they keep adding on as a result of these nuclear events. That's one type of nuclear waste, okay? That's the weird one, and that's kind of the scary one, okay? Because you can do really bad stuff with that. The other type is as a result of the fission event. Okay, when a uranium nucleus gets whacked by a neutron, okay, it splits in very predictable ways, okay? And those so-called daughter products are smaller, right? Because now I've split one big nucleus into smaller ones, okay? Those are the fission products, okay? Those aren't nearly as bad because you can't make a bomb with them. That's not weapons stuff, okay? Nevertheless, they do emit subatomic particles, and they can be around for a very long time, okay? So, I mean, I'm not calling it safe, but I mean, that's like kind of like the safer of the two, okay? Because you can still do really bad stuff with the transuranics. As a result of the nuclear fission, the incomplete nuclear fission, unfortunately, we can get stuff that is much heavier than uranium. Everybody knows about the most famous one, the plutonium, right? And so it took on 4 more nucleons, right? 2 protons, 2 neutrons, right? So plutonium is 2 further up from uranium, right? And it's gone to 239, which is the very bad one. 238 plutonium is actually a very useful one, but plutonium-239 is very bad. And so now that's 4 up from 235, right? So that had to occur in some fashion. And it turns out that there are other elements beyond that. But you can still do very bad stuff with plutonium, obviously. Neptunium, it was proved that you can make a nuclear device with neptunium. So you can do bad stuff with that. And then the other type is, as I had said before, the fission products, okay? They give off a lot of heat in the form of subatomic particles, usually beta particles. But you can't make a nuclear weapon with those. So they are long-lived. So those are the 2 types of nuclear waste. The heat, the fuel is its own coolant. We can expend all of the nuclear waste that we have using a little bit of pretreatment and then throwing it right in, just like a soup. It sounds silly, but that's pretty much what you're doing. There's some technical stuff that goes on and this and that, but I mean, how great would that be to get rid of all that waste? The 2 types of waste that I had said before, that are plaguing the people of Hanford, Washington right now. Because it's been sitting around and it's getting worse and worse and worse. Because now the tanks are starting to leak. Because they chose single-walled tanks. Why would you do that? That's a terrible engineering decision. That's a terrible chemistry or physics decision that was made in 1979 or 1981 when those tanks were built. Bad idea. You can burn up. I hate using that word. You can expend nuclear weapons by just throwing them into the soup. And the reason is that they will get expended, chewed up, very efficiently. There will be very little waste, almost no fissile waste, bad waste at the end. You will get a fair amount of fission products, okay? Of the long rectangle at the bottom of the periodic table, you can go YouTube or Google this, the upper row of the bottom rectangle are the so-called fission products. And those are isotopes, otherwise known as rare earths, but they are the radioactive versions of the rare earths. So that's why a molten salt reactor actually works so much more efficiently. You've got fabulous surface area because it's a liquid. So everything's touching everything else. It's one big soup. And you can get very efficient expenditure of that. And that, combined with the fact that it is a liquid, so it's moving. They basically fall into two camps with one little provision. Camp one is a true molten salt reactor where, like I said before, the fluid is both the fuel and the coolant. Zhangmin Hang and his project in China right now is with Westinghouse, and that is where the fuel is still solid, and the molten salt is being used merely as the working fluid, merely as the heat transfer medium. Those are the two groups right now. Okay? Per Peterson is also using the same design at Berkeley in concert with MIT and University of Wisconsin-Madison. That is where you use the molten salt as merely the working fluid or the coolant, and you still nevertheless have a solid fuel. Okay? David LeBlanc, basically the leading physicist in Canada, he talks about a true molten salt reactor. Okay? Using a fissile fuel as the molten salt where the fuel is its own coolant. Okay? He prefers to use LEU, low-enriched uranium-235. Kirk Sorensen has a design which is called a two-fluid reactor. The inner one is just like a molten salt reactor, okay, where the fuel is its own coolant, okay? But with his design, there is a blanket. And the blanket is, as we had discussed before, it gets a little technical, but as we discussed before, you need a kickstart. You need a kickstart for a thorium-based molten salt reactor. In his design, the outer blanket would serve as the starting point, if you will, because you're breeding the fissile kickstarter in the outer blanket. The lifter, as it's called, can't be built, cannot currently be built. Okay, so it is a great design, it's a fabulous design. I would love to see it work, but it can't be built. Okay? We don't know what the best material will be to permit the neutron flux to go out from the inner core, right? And to permit it to breed, okay? Make the fissile in the outer blanket. We don't have that wall material, that wall that separates the two. We don't know what the best material is yet. So it's a great design, but we need to get caught up on the material science and the metallurgy. That's probably the best way to go. Do we want to build this 1 gigawatt monolithic nuclear reactor? I don't think that that's a smart move. And there are many people that would agree with me. Kirk Sorensen, fabulous proponent of molten salt reactors. David LeBlanc. The Canadian military, who are very worried about defending their northern borders, now that basically we have an all-year-round passage along Canada's northern coast. There are a lot of people that think that a small modular reactor is a great idea. I'm one of them. Scale up. Bring in chemical engineers. They are trained to scale stuff up. The 10 megawatt original, I believe it was 10 megawatt, original molten salt reactor should easily be scalable. It should easily be scalable in terms of geometry changes or combined with materials issues. It should easily be scalable. 50 megawatt, 100 megawatt, 250 megawatt, probably 250 seems to be the sweet spot. But that's a great idea. From a strategic point of view, that is a decentralized energy grid. There are lots of advantages to having decentralized stuff under heavy guard, under heavy security, because you don't want any of the nonsense. But I mean, it is far easier to control something that small, and that because it's really small. I mean, it's not that very big, because you don't need a containment shell. So I mean, there's a lot of versatility in a small size because the energy density of this thing is very, very great. So the operative word is called a calandria. It's a tube within a tube, right? So the inner tube is where the fissile fuel is going, and then the outer tube is the so-called blanket. That's a great design. He patented, I think it's great. But even he doesn't know what that material is going to be. I have what I think would solve those problems. I have several candidates that would actually solve those problems. Candidate materials. So the actual wall, what atoms, what crystals, what molecules could potentially make up that wall that separates the outer and the inner. But it solves the three problems, okay? It solves the neutron problem, it solves the embrittlement problem, and it solves the corrosivity problem. In other words, the caustic environment, right? Permits the neutrons to go through, okay? You don't have to worry about this thing called embrittlement, and it can tolerate the harsh chemical and thermal environment. I think 5 years is a reasonable period of time. Is that aggressive as all hell? Yes. Would we use the existing materials that were actually used in the original molten salt reactor, the Hastelloy material? Yeah, so it was run at for 20,000 hours straight at over 800 Celsius. That's impressive. They did it without computers. They did it when I was 4 years old. They did it in 1974. They had no computers. They did the whole thing. That to me is unimaginable. That to me is pioneering science. In 1948, the really, really great American chemist Glenn Seaborg discovered the decay chain for thorium. I won't go into the technical issues, but it is a very, very interesting decay chain, starting with thorium and going all the way down in terms of it being fissile events all the way down. That was pretty remarkable. And then, with the help of Alvin Weinberg, basically started the molten salt reactor project in 1951 at Oak Ridge National Laboratories. It began in 1951 and went all the way up to somewhere around 1974 or 1976 and went down pretty bad, pretty hard. It is well known that there is excellent expenditure for energy in terms of the molten salt as fissile fuel. And a lot of that had to do with how to contain a molten salt that's at somewhere around 600 Celsius, which is like 1100 Fahrenheit. How to contain something that is basically nuclear events that are occurring, enormous amounts of heat coming off. Oh, and by the way, it's in a ridiculously caustic medium because it is a molten fluorinating salt. Fluoride is at the heart, fluorine, the element, is at the heart of this because they are all salts. As I said, it's a molten salt. And it's a very unique type of chemistry that's going on. But anything at 600 Celsius that has to do with halide salts is pretty nasty stuff. So a lot of what they were focusing on was how to contain this. And there was a lot of excellent research that was done. And there was a lot of very interesting materials that actually arose as a result of all the research that occurred beginning in 1951 and moving all the way forward. So they got up all the way into the MSRE, kept moving and moving and moving, and unfortunately got swallowed up by the political game. Hyman Rickover was the bulldog, and he did a great number of things for the United States. He was an outstanding leader. Unfortunately, he muscled through PWRs, pressurized water reactors. A nuclear reactor is a fabulous power plant in order to get something going, like an aircraft carrier or like a submarine. I mean, it's outstanding, and that was a great move. A lot of scientists just believe, with very, very good scientific reason, not political reason, that he could have chosen a better system. We used solid fuel reactors ever since the first commercial reactor came online in 1958, okay? They are a fabulous energy source with lousy thermodynamics. And so we're stuck with what we have. We as humans are smart enough to create for ourselves a robust, sustainable, well-diversified, clever energy landscape. That's important, okay? I personally think that nuclear is a fabulous, and a molten salt reactor nuclear platform is a fabulous way of doing it. We just need to become aware, have some sort of critical mass, become aware as a species of what's going on around us. Because as a chemist and scientists in general, we look at the abstract. We understand what's going on an atomic level, or in some cases, a subatomic level. But that's really hard to convince a community of humans of stuff that's happening that we can see, that is plain as the nose on my face from a scientific perspective. It's really tough to convince that. It's really, really hard. And then you throw in the prospect of money, and it's much, much harder. That's why people like me, who like the idea of a molten salt reactor platform, I want to do it in a free market manner. I can make it profitable. I can manufacture them profitably. And I can create thousands and thousands of jobs here in the United States as well as abroad. So everybody wins.